Welcome to this video on buffer calculations. Previously we looked at buffers, and you should be able to remember that a buffer is made of a weak acid and its conjugate base, or a weak base and its conjugate acid. So here we have this one, the weak acid and the conjugate base, and to be honest, most questions you'll get will be to do with the weak acid, just because they're usually easier to understand. So here our weak acid is the methanoic acid and the conjugate base is methanoate. We've also got given here the Ka value, which we're going to need shortly. The first way to approach this is to use an ice table. There's actually three ways we'll look at, but the first one is the ice table. So here we've already put in the acid, the HCOOH. This is methanoic acid. We've got here our H plus ion, which is what we're mostly interested in, and then we have the methanoate ion here. We've got the usual rows here of the initial, change and equilibrium, and the initial is already filled in with details from the question. So we've got the 0.5 molar here, we've got the 0.2 molar here, and then remember this starts with 0. There will be hydrogen ions obviously in the water, but we don't use those in this kind of calculation. Next, the change. Remember that a little bit of the acid has to go to make the products, so we need to take a little bit away, which we normally call X. And on this side, we're going to add some X to both of these. Lastly, the equilibrium is going to be just the first two all combined together. So this one's just X. And lastly, we got 0.2 plus X. Next step, we need to write the Ka, the equilibrium expression, which is Ka equals to H plus times the concentration of the methanoate all over concentration of methanoic acid, like so. Next, we actually substitute the numbers. So first of all, the Ka value, and that equals to, well, this is X, multiplied by 0.2 plus X, all over, whoops, all over 0.5 minus X. Make those a bit nicer. Right, next, or the next steps are just rearranging this equation. So bring the 0.5 onto this side, 0.5 minus X onto this side. And then this one we're going to multiply through, so we get 0.2x plus x squared. Multiply this one out. 1.8 times 10 to the minus 4 times 0.5 is just 0.9 times 10 to the minus 4. And before you say anything, we could actually just make this 9 times 10 to the minus 5. That's also correct. I'm just keeping it in the same just to make it simpler. Next, this one is 1.8 times 10 to the minus 4 x equals that. Next, we rearrange and put these onto the other side, leaving 0 here. So 0 equals, and I'm going to put these in the correct order, x squared plus 0.2x, and then plus 1.8 times 10 to the minus 4x, and minus that little one there. Okay, very last bit before we do the calculation, just tidy this up. So we get x squared plus 0.20018. So it's quite a small change to the 0.2. X minus 0.9 times 10 to the minus 4. Right, and if you do the calculation for the quadratic equation using the quadratic formula, which I'm not going to show you because you know how to do this, you should get x equals 0.000444859 or something similar, and 0.20062859. Now, we normally get two of these numbers. Remember, sometimes you may get one. That's really unusual. Sometimes it might be undefined, in which case you've probably done something wrong. In this case, we've got the minus here. It could be the minus, but then if we look at this properly, and if we go through the effect on the numbers, you can see clearly it can't be this, because on this side we'd add to the methanoic acid, which usually we can't do, but we had the methanoate here. But if we minus 0.2006, etc., from this, we'll end up with minus amounts. Same for the H+. So we cannot have this number. So this is our answer. And I'm going to round that up and put that in here because this is x as well. So let's round it up. 0.045, which means that this value is 0.20045, and this one 0.5 minus that number is 0.49955. You should be able to see this is a very small deviation from 0.5, and this one is a very small deviation from 0.2. Right, anyway, this is the number we're interested in. We actually don't care about these two too much, but this one is the number we're interested in. So the last thing we need to do, remember what it says here, the pH. So this is not an answer. You need to give it in pH. pH equals, and if you remember, that's minus log of this number, 0.0045, and that gives us approximately 3.3. Right, is it worth giving any more decimal places than this? The answer is no, for two reasons. The first is, if we look at the initial question, we've only got 0.5, one decimal place here and one decimal place here. In fact, one significant figure for both of these. So the answer cannot be too precise. In fact, this is probably too precise for the information we've got. Another thing is, you've also got to remember that we're going to be doing this in real life, and there's going to be lots of problems with experimental error and the like. So actually, it's not that crucial to be much more accurate than this. Most of the time in the lab, it will be to 2 dp, maybe 3 dp at the most. So let's put a line in here. And what I'm going to do here is show you an approximation. Remember I said on this side we have a very small deviation from 0.5 and a very small deviation from 0.2. So if we go back to this bit and do this again, so 1.8 times 10 to the minus 4 equals x multiplied by 0.2 plus x all over 0.5 minus x. This deviation is so small compared to what this number is that we can ignore it. Also, this number here is very small compared to this number, so we can ignore it as well. Remember, we did this cheating method before. Now look what effect that has on the equation. So we've now got the equation here, and we've still got the 1.8 times 10 to the minus 4 there. We now have 0.2x here and 0.5 on the bottom, instead of this horribleness. That means the next steps are much easier. So the next step would be multiply by 0.5 would give you the 0.9 times 10 to the minus 4 equals 0.2x. Lastly, that divided by 0.2. And there we are. It's actually a lot quicker, a lot simpler, and especially for chemists, it's much more understandable than doing all these quadratic equations and stuff. So that gives us an answer of, you guessed it, 0.0045, which is pH, and I don't need to calculate this again because I've done it already, 3.3. Now granted, this won't be as accurate as the first method, because in the first method we actually rounded it up in the calculation steps, whereas here we get the rounded version straight away, but it hasn't made much difference to our answer. And you can check this out yourself. If you leave this number in the calculation and do the minus log of that number, you'll see it be something like 3.346787 blah 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 blah. So practically there's no real difference between them. So that is the second method, and I'm hoping you can see it's a lot simpler. Right, one last thing I want to show you, write it down here, is an equation which is this: the pH is equal to pKa, which is the minus log of the Ka, plus the log of, and we're going to have here the A minus over HA. So that A minus, if you remember from the equation, I'll put the equation up here in a minute, but from the equation this stands for the conjugate base and this is the acid. So if I rewrite that here, pH equals pKa plus log of the concentration of the methanoate, in our case, over the concentration of the methanoic acid, put that in bracket, and then we fill in the details. pH equals minus log of 1.8 times 10 to the minus 4 plus the log of, and what do we have? Well, 0.2 over 0.5. Okay, so this time we have used an equation, and if you calculate this out, you'll get pH is 3.3. And this equation here is called the Henderson-Hasselbalch Equation. And this is the one you will be using most often, to be honest, and this is the one that's used in the lab. As I said before, most of the time we don't want super accurate results of the pH. You want around 1 decimal place, 2 decimal places, 3 decimal places is quite unusual. And this method, unless the Ka value is particularly different than what we normally get for weak acids, then it should be okay. You still should do a check to make sure it's okay. This should still be a very small number, but in most of the questions you get asked, this is perfectly adequate as an estimation of the pH. So the kind of questions you're going to get are going to ask you to do either the ice table or the Henderson-Hasselbalch equation, and I'm actually going to explain now how the Henderson-Hasselbalch equation is derived. This isn't necessary for you to know, but if you're interested, keep watching. If you're not, then you should have enough information to be able to do the questions. This section is going to look at the Henderson-Hasselbalch equation and going to show you how to derive it. First thing we need to do is remind ourselves of the expression, the equation for the dissociation of a weak acid, which is what we used for our buffer. So we've got HA, which is our acid, breaks down to the H plus and the conjugate base. Remember, the buffer supplements the conjugate base. And if we write that in the equilibrium expression, we get, do it here, Ka equals H plus concentration times by the A minus concentration all over HA. Right, what we're going to do here is rearrange it and show you how you get the equation. So the first thing we need to do is multiply it by the HA at the bottom. So we get this one like this, and this H plus and the A minus stays on that side. Next thing we do is, remember, we want to find the pH, so we want the H plus on its own. So next step is we divide by A minus, so we get this divided by A minus equals H plus. Right, excellent. So I'm just going to rearrange that. So we've got the H plus on the correct side. And here I'm also going to just take out the Ka so you can see exactly what we're going to do next. So that is Ka multiplied by HA over A minus. You can write it like this. The next thing we need to do is turn this into pH. So pH, if you remember, is the minus log of H plus. So what we can do next is do the minus log of H plus. But if we do it to this side, we must also do it to everything else. So let's just put a bracket around that. Over A minus. Now, one of the rules of logarithms, oops, forgot the bracket. One of the rules of logarithms is if you've got log m times n, that can be made into log of m plus the log of n. So here we've got Ka times this. So on this side, what we can do is separate them out. Now this one here, I'm actually going to substitute straight away so we can kind of make it nicer. The minus log of H plus is the same as pH. On this side, we then have the minus log of our Ka, and because it's multiplied by that, we can replace it by A plus. That's meant to be an A. Put a bracket around that as well. Ka plus the log of HA over A minus, like so. Now the next step, so I'm going to just put the minus into both in a second. So we got pH equals minus log of Ka. Now this can be changed into pKa, which is a value we use quite often. And then we got minus, and again I'm going to put it in brackets, log of. Now this one here is a different rule, which is the division rule. If you've got m over n, then that gives you log of m minus log of n. So let's change that. Minus log of A minus. And remember that was all minused. So next step, we're going to just write this out again. So we've got pH equal, this bit here becomes pKa, which is an important number that we can sometimes use. And this bit will become minus log HA plus log of A minus. Right, unfortunately with these last two we can't do much with them. There's no way we can tidy them up. So what we're going to do instead is put them back together. And here you should see that we can actually rearrange this to give you pH equals pKa plus log of A minus log of HA. Just put them back into the nicer order. But we now got this bit here, which using the rule, this rule at the bottom, we can then turn back into, you guessed it, pH equals pKa plus the log of this one, A minus, over HA. Just going to put that in brackets, make it clearer, and look at that, we've got the same as this. Now I did tell you before that there's two forms of this equation, and that's true. I'm only showing you the one because both of them do the same thing. But you need to be aware that if you're on the internet, you might find actually the version I kind of got to here, we could have stopped and had minus log of HA over A in this form. But I don't want you to get confused and just want you to remember one version and use that, because both of them do the same thing. One last thing to finish up with is normally in the data tables, when you're looking up the values for the acid dissociation, you do not find it as Ka. Instead, you'll find it as pKa normally. This means you have even less work to do when you're using the equation, because you then literally put the pKa value straight into the equation and use that. So that makes this equation even more useful. Right, so that pretty much covers everything for buffer calculations. Hopefully you now be able to do this kind of calculations when you come to it. And I hope that made everything clearer.